A star detonates with the force of 100 billion suns. This ferocious violence is also the universe's greatest act of creation. We are about to journey into the heart of cosmic explosions, from supernova to hypernova, to uncover 28 incredible facts. By the end, you will see the cosmos not as a static picture, but as a living, breathing, and often explosive arena. We will discover how the gold in a wedding ring was forged in a stellar cataclysm and confront the terrifying power of a gamma-ray burst. What do you believe is the true legacy of a dying star? That single blast of cosmic violence can release more energy in a handful of seconds than our own sun will muster across its entire 10 billion year life. Think about the sheer scale of that for a moment. Our sun is a continuous nuclear furnace that has bathed our solar system in light and warmth for billions of years, and it will continue to do so for billions more. Every single second of its existence, it expends a staggering amount of power. Now, imagine compressing the total energy output of that entire epic lifetime into the time it takes you to read this sentence. This is the incomprehensible power of a gamma-ray burst. To put it in a more terrestrial perspective, if you gathered every nuclear weapon ever built and detonated them all at once, the energy released would be a whisper compared to the roar of one of these events. You would need to multiply that cataclysmic earthly explosion by trillions upon trillions to even begin to approach the fury of a gamma-ray burst. This single fact forces us to completely abandon our earthly notions of power and violence. Our most destructive creations are but a flicker in the wind compared to the true forces at play in the cosmos. That gold in your jewelry or the uranium fueling power plants was not made in the calm heart of a star. It was forged in chaos, deep within the final moments of a supernova. A storm of nuclear fire rages. For most of its life, a star is a careful craftsman, slowly fusing hydrogen into helium, then helium into carbon and oxygen, all the way up to iron. But iron is a dead end. Fusing iron does not release energy, it consumes it. The star's central furnace suddenly sputters and dies. With no outward pressure to hold it up, the star's own immense gravity crushes its core in a fraction of a second. This collapse triggers a rebounding shockwave of unimaginable violence, a blast that rips the entire star apart. In that fleeting, hellish inferno, temperatures and pressures soar to levels we cannot replicate on Earth. Atomic nuclei are bombarded by a frantic sea of neutrons, glomming on one after another in a frantic process called rapid neutron capture. It is in this frantic, explosive capture that ordinary iron is transformed. It becomes silver, platinum, lead, and gold. Every heavy atom in our world, from the iodine in your body to the uranium that can power a city, is a literal piece of stardust, a shrapnel fragment from an explosion that happened long before our sun was even a glimmer in the galaxy. So the next time you hold something heavy and metallic, consider its incredible journey. It was born in a cataclysm that outshone entire galaxies, a violent end that became the essential beginning for planets and for life itself. But not all stellar deaths are the same. The universe has more than one recipe for destruction. Astronomers classify these titanic explosions into two main families, each with a distinct origin story and a unique fingerprint of light. The first, known as a Type II supernova, is the final dramatic collapse we just explored. It is the fate of stars at least 8 times more massive than our Sun, whose cores run out of fuel and implode under their own weight. The light from such an event often shows a strong signature of hydrogen, a telltale sign of the star's outer layers being blasted into space. Then there is the Type I, a supernova, a completely different kind of detonation. This one begins not with a giant star, but with a corpse, a white dwarf, the incredibly dense remnant of a sun-like star. can lurk quietly for billions of years. But if it has a companion star in a binary system, it can begin to steal material from its neighbor. The white dwarf gorges itself, growing heavier and hotter. Eventually, it reaches a critical mass, a tipping point known as the Chandrasekhar limit. In a single, runaway thermonuclear instant, the entire white dwarf is obliterated. No core collapse, no neutron star left behind. It is completely vaporized in a blast of pure atomic fire. This fundamental difference in their nature gives Type 1, a supernova, a remarkable property. Because they all explode at almost the same critical mass, they all reach nearly the same peak brightness. This makes them cosmic lighthouses, what astronomers call standard candles. When you see a lighthouse, you know its intrinsic brightness, so by measuring how dim it appears from your location, you can calculate how far away it is. In the late 1990s, two teams of astronomers used these stellar lighthouses, these Type 1, a supernova, to measure the expansion of the universe. They expected to find that the pull of gravity was slowing the cosmos down. To their astonishment, they discovered the opposite. The universe is not just expanding, it is accelerating, flying apart at an ever-increasing rate, driven by a mysterious force we now call dark energy. This monumental discovery, which earned a Nobel Prize, hinged entirely on the predictable, self-destructive nature of a certain kind of stellar explosion. Yet the brilliant flash of light we see is only a tiny fraction of the story. When a massive star collapses, the true engine of the explosion is almost invisible. A staggering 99% of the total energy released does not come out as light, but is instead carried away by an unimaginable flood of ghostly particles called neutrinos. These are among the most elusive and strange entities in the universe. They are so ethereal that they can pass through light years of solid lead without a single interaction. And every single second, trillions of these cosmic phantoms, mostly from our own sun, are streaming straight through your body and through the Earth itself, leaving no trace at all. This ghostly nature made them almost impossible to detect, but in February of 1987, our models of stellar death were put to the ultimate test. A star went supernova in our galactic backyard, the Large Magellanic Cloud. Just hours before the light of supernova 1987 reached Earth, two enormous underground detectors, one in Japan and one in the United States, registered a sudden, brief pulse. Over a span of just 13 seconds, they captured a total of 24 neutrinos. This was the ghostly signal from the heart of the collapsing star, arriving right on schedule and confirming a critical prediction. Those 24 fleeting interactions, out of the untold trillions of particles that passed by, were our first direct telegram from the heart of a supernova. They proved that our understanding of the core collapse, the very moment a star dies, was fundamentally correct, but the supernova we just explored is not the final word on cosmic destruction. For the most massive stars in the universe, death comes in an even more extreme form, a supernova known as a hypernova. These are the final, apocalyptic cries of stellar behemoths, stars that begin their lives with at least 30 times the mass of our Sun and are often spinning at a ferocious rate. Their end is not a simple core collapse into a neutron star, but a total and utter demolition. The core, under such immense gravitational pressure, bypasses the neutron star stage entirely and plummets directly into the abyss, forming a newborn black hole in an instant. This is where the true spectacle begins, governed by what astronomers call the collapsar model. As the stellar material swirls into the nascent black hole at near light speed, it forms a searingly hot, dense disk of accreting matter. The incredible rotational energy and powerful magnetic fields of the star are now focused into two narrow, opposing jets, firing out from the poles of the collapsing system like cosmic blowtorches. These are not gentle streams of gas, they are ultra-relativistic jets, beams of particles and radiation moving at 99.9% the speed of light, carrying with them the gravitational binding energy of the black hole itself. And if one of those jets is pointed by chance directly at Earth, we witness the single most energetic electromagnetic event known to occur in the entire universe. We see a long gamma-ray burst. For those few precious seconds, this narrow beam outshines every star, every galaxy, every other source of light in the cosmos combined. The hypernova is the engine, and the gamma-ray burst is its terrifying, focused scream across the void. That focused scream of a gamma-ray burst is more than just a cosmic spectacle. It is a genuine threat, a hypothetical doomsday scenario that astronomers take seriously. If one of these events were to occur within a few thousand light years of Earth, and its deadly jet was aimed directly at us, the consequences would be catastrophic. The initial blast of gamma rays and high-energy particles would not just be a light in the sky, it would slam into our atmosphere with the force of a nuclear bomb detonating over every square mile of the planet's surface. This immense energy would rip apart the molecular bonds in our upper atmosphere, initiating a chain reaction of chemical destruction. The primary casualty would be our planet's ozone layer. This thin, gaseous shield that protects all life from the sun's harmful ultraviolet radiation would be utterly obliterated. Within days, it would be stripped away, leaving the surface of the Earth exposed to a lethal bath of UV light. The results would mirror the worst extinction events in our planet's history. Phytoplankton in the oceans, the base of the marine food web, would die off. Land plants would wither. Animals, including humans, would suffer severe radiation burns and a dramatic increase in cancer rates. The ensuing ecological collapse could lead to a mass extinction. Now, it is crucial to state that the probability of this happening is incredibly, astronomically low. The stars that can produce such bursts are rare, and their jets are incredibly narrow. The chance of one both forming nearby and having its deadly beams sweep across our solar system is vanishingly small. We are living in a relatively quiet suburban neighborhood of the Milky Way, not in the violent downtown core where such events are more common. But this terrifying possibility serves as a stark reminder. It underscores that we exist in a dynamic and sometimes dangerous cosmos, where events occurring unimaginable distances away can, in theory, reach out and touch us. Our survival on this pale blue dot is contingent on the continued quiet of our galactic neighborhood. The debris from these explosions does not simply drift away. It becomes an engine of its own, a natural cosmic accelerator of unimaginable power. The expanding shell of a supernova remnant, racing outward at thousands of kilometers per second, creates a violent shockwave that plows through the interstellar medium. Within this chaotic frontier, tangled magnetic fields act like a vast natural particle accelerator. They can fling protons and atomic nuclei to velocities approaching the speed of light, energies that make our most powerful human-built machine, the Large Hadron Collider, seem like a child's toy. These accelerated particles are known as cosmic rays, and they are a constant, invisible rain upon our world. Right now, as you listen, these subatomic bullets are piercing through the atmosphere, through the roof above you, and through your own body. They are mostly harmless, but they are a tangible reminder that we are connected to these distant cataclysms. The most famous of these cosmic engines is the Crab Nebula, the glittering aftermath of a supernova observed by Chinese astronomers in the year 1054. Its heart pulses with a spinning neutron star, and the entire nebula glows with the light of these accelerated particles, a permanent testament to the creative destruction of a stellar death. By stirring up the gas between the stars and seeding it with heavy elements and energetic particles, supernova remnants shape the very conditions for future star birth. They are the great recyclers of the galaxy, ensuring that the death of one star becomes the raw material for the next generation. This predictable self-destruction is what makes them so invaluable to science. A Type 1, a supernova, is a cosmic mile marker, a standard candle whose true brightness we know with remarkable precision. When astronomers observe one of these explosions in a distant galaxy, they can measure how bright it appears from Earth. Just as a distant lighthouse appears dimmer than a nearby one, a fainter supernova must be farther away. By carefully measuring this apparent dimness across vast cosmic distances, they can construct a three-dimensional map of the universe's expansion over billions of years. In the late 1990s, two independent teams set out to do exactly this. They were not looking for a revolution, they were simply trying to measure how much the universe's expansion was slowing down due to gravity. They painstakingly collected data from distant Type 1, a supernova, expecting to see that the most ancient explosions were a little brighter than standard cosmology predicted, indicating they were closer because expansion was faster in the past and has since slowed. The data told a completely different and frankly unbelievable story. The most distant supernova were not brighter than expected, they were fainter. Much fainter, this could only mean one thing: those supernovae were farther away than anyone had calculated. The universe's expansion was not slowing down at all. It was speeding up, some mysterious repulsive force, counteracting gravity on a cosmic scale, was pushing galaxies apart at an ever-increasing rate. This force, completely unknown and unexpected, was dubbed dark energy. The discovery was so shocking that the teams spent years checking and rechecking for errors, for some hidden flaw in their measurements or in the nature of the supernova themselves. But the result held firm. In 2011, the leaders of these projects were awarded the Nobel Prize in Physics for this monumental finding. A specific type of stellar explosion, a predictable cosmic bomb, had revealed that the fate of our entire universe is being shaped by a mysterious, dominant force we cannot see and do not understand. We cannot hear the explosion itself, for sound cannot travel through the emptiness of space, but a supernova still creates its own kind of symphony. The blast sends a colossal pressure wave rippling outwards at thousands of kilometers per second, a supersonic wall of force that plows into the surrounding clouds of interstellar gas and dust. This is the supernova's true voice, a vibration traveling through a tangible medium. Astronomers can even translate this phenomenon into something we can perceive. Using a process called data sonification, they assign musical notes to the changing intensity of light or the density of gas within these expanding remnants. What you hear is not a literal recording, but a translation of the data, a ghostly melody that represents the shockwave's journey. It starts with a deep, powerful boom that slowly gives way to shimmering, ethereal tones as the wave expands and dissipates. This is the echo of a star's death, played back for human ears, but this cosmic sound wave is far more than a haunting melody. As it travels, it compresses the vast, tenuous clouds of hydrogen gas, squeezing them in its path. These clouds, once stable and diffuse, are suddenly pushed over a critical threshold. Their own gravity, now amplified by the external pressure, takes over. The cloud begins to collapse, fragmenting into dense knots that ignite under their own weight. In this way, the shockwave from a single, violent death acts as a cosmic trigger for the birth of new stars. The supernova's destructive roar literally becomes a nursery's first lullaby, a perfect demonstration of the universe's endless cycle of creation from destruction. While the death of a single star is a potent creator, a far richer alchemy occurs when two stellar corpses decide to merge. This event is known as a kilonova, and it represents a cosmic forge of unparalleled power. On August 17, 2017, a new chapter in astronomy was written. For the first time, gravitational wave observatories felt the telltale ripple in spacetime caused by the final, frantic orbits of two neutron stars spiraling together. Just 2 seconds later, space-based telescopes detected a flash of gamma rays from the same patch of sky. The race was on. Ground-based observatories across the globe swiveled to look, and what they found was a new, brilliant point of light in a distant galaxy, glowing with the heat of a radioactive fire. This event, catalogued as GW 170817, was the first ever multi-messenger observation of a cosmic cataclysm. We not only felt the space-time shudder of the collision, but we also saw the brilliant, radioactive aftermath with our own eyes. The data revealed an incredible truth. The intense environment of a kilonova, with its insane densities and abundant free neutrons, is the universe's primary factory for the very heaviest elements. In the swirling debris of that collision, rapid neutron capture ran wild, producing a staggering amount of precious metals. A single kilonova is thought to forge an amount of gold and platinum equivalent to several times the mass of our entire planet. So every gold ring or platinum necklace is not just stardust, it is likely the specific, tangible remnant of a cataclysmic merger that happened billions of years ago, a violent union that seeded our cosmic neighborhood with the ingredients for worlds and life. The universe holds mysteries that make even gamma-ray bursts seem almost conventional. Meet the fast radio burst, a flash of radio waves so brief it could be over in the time it takes to blink, yet it carries the power of 500 million suns. These events appear as sudden, intense spikes on radio telescopes, lasting only a few thousandths of a second before vanishing without a trace. They come from galaxies billions of light years away, and for years after their discovery, they were a complete enigma. What natural process could possibly generate such an immense amount of energy and release it all in a single, fleeting pulse? The leading suspect today is a type of stellar corpse we have already met, but pushed to an even more extreme limit, the magnetar. Imagine a neutron star, an object so dense a teaspoon of it would weigh 1 billion tons, but then amplify its magnetic field to a level that is almost pure fiction. A magnetar's magnetic field is 1,000 trillion times stronger than Earth's. It is a field so powerful it could strip the information from every credit card on the planet from halfway across the solar system. The crust of a magnetar is under unimaginable strain, and it is thought that a sudden rupture, a starquake, can crack this solid surface, releasing a titanic shockwave of energy that we see as a fast radio burst. Yet even this incredible explanation may not account for all of them. Some bursts are one-off events, while others repeat sporadically, defying a simple starquake model. The puzzle is so profound that some scientists, cautiously and with many caveats, have not ruled out an even more astounding possibility. Could these focused, powerful bursts be the leakage from unimaginably advanced technology, perhaps powering the light sails of interstellar spacecraft? While this is the least likely answer, its mere consideration highlights how utterly these events challenge our understanding of physics. They are cosmic flashes in the pan that force us to question everything we know about energy and matter. The magnetic field of a magnetar is a force of pure distortion. It warps reality itself, creating an environment so extreme that the very shape of an atom is torn apart. If you could venture within a few thousand kilometers of one of these stellar corpses, the magnetic field would be so overwhelmingly powerful that it would squeeze the spherical cloud of an atom into a long, thin, needle-like shape. Atoms, the fundamental building blocks of all matter, simply cannot maintain their structure under such an onslaught. This is not merely a strong magnet, it is a fundamental force of nature made manifest. These objects are born from the chaos of a supernova in a specific type of star, one that was both massive and spinning rapidly. As the core collapses, it concentrates the star's original magnetic field, amplifying it to almost unimaginable levels. The resulting magnetar is a neutron star, but one dialed up to 11, possessing a magnetic field a quadrillion times stronger than the field that protects our own planet. And this unimaginable power is not dormant. The magnetar's solid crust, a lattice of iron nuclei under immense strain, is constantly stressed by the magnetic forces twisting within. Occasionally, this tension becomes too much to bear, the crust cracks. This starquake is a seismic event on a cosmic scale, releasing more energy in a fraction of a second than our Sun will emit in 100,000 years. The result is a catastrophic rebinding of the magnetic field lines, which unleashes a blinding flash of gamma rays and X-rays, a flare that can temporarily outshine every other source in our entire galaxy. These are not the focused jets of a gamma ray burst, but terrifyingly brilliant, all-sky eruptions that remind us of the raw, untamed power lurking in the dark. That ancient flash in the sky was a direct message from a dying star. In the year 1054, a new star blazed into existence in the constellation of Taurus. Chinese court astronomers, meticulous watchers of the heavens, recorded it in stunning detail. They called it a guest star, noting it was visible in broad daylight for 23 consecutive days and remained bright enough to see with the naked eye at night for nearly 2 years before it finally faded from view. Arab and Japanese stargazers also documented this sudden, brilliant visitor, an event that would have been both awe-inspiring and deeply unsettling to cultures that saw the sky as eternal and unchanging. They were witnessing a supernova, the explosive death of a massive star some 6,500 light-years away. Today, we can point our telescopes to that exact spot in the sky and see the aftermath. The Crab Nebula is a beautiful, tangled web of glowing gas, expanding outward at over 1,000 miles per second. At its heart spins the dense corpse of that original star, a pulsar that rotates 30 times every second, flashing like a cosmic lighthouse. This direct link from an ancient observation to a modern astronomical object gives us a rare and precious timeline. We know exactly how old this stellar remnant is, allowing us to study the entire life cycle of a supernova, from its brilliant flash to its slowly expanding, glittering debris cloud. The Crab Nebula is not just a picture in a textbook, it is a living, breathing crime scene, and we know precisely when the cosmic explosion occurred. Sometimes the universe stages a brilliant dress rehearsal for its final act. Not every titanic outburst in the cosmos is a true death. Some of the most luminous events we observe are actually supernova imposters, colossal eruptions from unstable stellar giants that tear themselves apart without fully dying. The most famous of these is Eta Carinae, a volatile binary star system located about 7,500 light-years away. In the 1840s, this star underwent what astronomers call the Great Eruption. For over a decade, Eta Carinae became the second brightest star in the entire night sky, outshone only by Sirius. Despite its immense distance, it ejected an enormous amount of material, forming 2 vast, expanding lobes of gas that we see today as the Homunculus Nebula. This was not a supernova, but a monstrous stellar temper tantrum. The star survived, though it was left profoundly changed, shrouded in its own dusty wreckage. So what causes such a violent, non-fatal explosion? In stars like Eta Carinae, which may be over 100 times the mass of our Sun, the radiation pressure from within becomes so intense that it begins to overpower the star's own gravity. The outer layers become unstable, puffing up and ejecting massive shells of material in sporadic, eruptive events. It is a star literally fighting to hold itself together against its own immense power. These imposters are a preview, a warning of the true cataclysm to come. Eta Carinae is a ticking time bomb, destined to end its life in a spectacular supernova or even a hypernova, possibly within the next million years, a mere blink in cosmic time. When it finally does go, it will be a celestial spectacle for the ages, visible even in our daytime sky. Could the universe's greatest explosions be fueled by its most elusive substance? While we understand the mechanics of standard supernova, some recent observations defy all expectations. Astronomers have detected a class of superluminous supernova, stellar explosions that are up to 100 times brighter than they should be. These are not mere outliers, they are cosmic anomalies that shine with an intensity that our current models of nuclear physics simply cannot explain. Where does all that extra energy come from? One of the most fascinating, though highly speculative, theories points to an invisible culprit, dark matter. This mysterious substance, which makes up about 85% of the matter in the universe, only interacts with normal matter through gravity. We know it's there, but we have never directly detected it. The hypothesis suggests that in certain dense, ancient stars, dark matter particles could accumulate in the core over billions of years. If these particles are of a specific type, they could be their own matter and antimatter counterparts. When such a particle meets its opposite, they would annihilate each other in a flash of pure energy, just as normal matter and antimatter do. Now imagine a star's core becoming a furnace not just for nuclear fusion, but for dark matter annihilation. As the star ages and its core becomes denser, it could draw in and trap more and more of these dark particles. At the critical moment of collapse, this hidden reservoir of dark energy would ignite, supercharging the explosion from within. The resulting blast would be far more violent and luminous than a standard core collapse supernova, potentially explaining the freakish brightness of these events. This idea remains on the fringe of astrophysics, a tantalizing possibility that has not yet been proven, but its very existence reveals a profound truth about our quest for knowledge. When we witness something in the cosmos that we cannot explain with our current understanding, we are forced to invent new physics. These impossibly bright supernova are not just dying stars, they are beacons, potentially illuminating the path to finally understanding the dark heart of our universe. The cow was an astronomical event that simply refused to follow the rules. In June of 2018, a survey telescope in Hawaii spotted a sudden flare in a distant galaxy. It was designated at 2018 Cow, a random string of letters that quickly earned it the memorable nickname, the Cow. At first glance, it looked like a supernova, but its behavior was bizarrely alien. It exploded into brightness with shocking speed, reaching a peak luminosity far greater than a typical star's death, and then its light faded away in just a matter of days, not the months or years expected for a supernova. It was as if a cosmic bomb had gone off with a brilliant flash and then vanished before anyone could properly identify it. The event also emitted a tremendous amount of energy across the spectrum, from high-energy X-rays down to radio waves, a broad spectrum of fury. The astronomical community scrambled for an explanation. Was this a star being shredded and devoured by a previously dormant black hole, or was it the birth of a black hole or a magnetar, where a collapsing star's core funnels its energy into a fast-moving jet of debris that we happen to be looking directly down the barrel of? The cow forced astronomers to confront a simple truth: we have not yet cataloged all the ways the universe can explode. It represents a new class of cosmic transient, an entire family of rare, incredibly energetic, and fast-evolving events that we are only now beginning to detect with our automated sky surveys. Each one is a puzzle, a clue that our map of stellar death is still missing entire continents of discovery. Our own planet's history is written in the light of distant stellar deaths. There is compelling geological evidence that nearby supernovae have directly intervened in Earth's story, leaving their radioactive signatures deep within the ocean floor and in lunar soil. Scientists have found layers rich with an isotope of iron, iron-60, which is forged almost exclusively in supernova explosions. This radioactive dust, settling across the solar system, acts as a cosmic timestamp, pointing to periods over the last 10 million years when one or more stars exploded frighteningly close to our world, perhaps as near as 150 light-years away. Imagine the sky in those eras, suddenly hosting a second, temporary sun visible even during the day, its light shining for weeks or months, but the effects would have been far more than just a spectacular light show. The incoming blast of radiation and high-energy particles could have stripped away parts of our atmosphere, damaging the ozone layer and showering the planet's surface with increased cosmic rays. This could have triggered climate shifts and raised background radiation levels, potentially influencing the course of evolution by applying a subtle, persistent pressure on living organisms. It is a humbling thought that a catastrophe occurring light years away may have helped steer the destiny of life on our planet. We are not just observers of this cosmic drama, we may be characters whose very existence was shaped by its most violent acts. This influence extends to the very space our solar system travels through. We reside within a vast, cavernous region known as the local bubble. This is not a void, but a 700 light-year wide cavity of incredibly hot, thin, low-density gas, a blister in the spiral arm of our galaxy. The walls of this bubble are sculpted from cooler, denser gas and dust, the very nurseries where new stars are now forming. How did this colossal cavity form? The prevailing theory is a story of sequential, catastrophic violence. Roughly 10 to 20 million years ago, a string of perhaps 20 or more supernovae detonated in a nearby stellar cluster. One by one, their immense shockwaves expanded, pushing the interstellar medium outward like a cosmic snowplow, piling it up at the edges and hollowing out the space around them. Our solar system, on its journey around the galactic center, drifted into this cleared-out region only about 5 million years ago. The local bubble is our local cosmic environment, a legacy of ancient stellar cataclysms that created a protective, if turbulent, pocket in the galaxy. It is the cleared stage, shaped by generations of exploding stars, on which our solar system now performs its long, slow orbit. Hanging in the constellation Orion, the red supergiant Betelgeuse is a ticking time bomb. This colossal star, so vast that if placed at the center of our solar system, it would engulf the planets out to Jupiter, is a prime candidate for a core collapse supernova. Its final years have been marked by dramatic and unpredictable dimming events, moments when its light noticeably faded, sending ripples of excitement through the global astronomy community. These episodes were not the final act, but likely belches of stellar dust or massive convective cells on its turbulent surface, a star showing the unmistakable signs of its impending demise. When the core of Betelgeuse finally does exhaust its fuel and collapses, the resulting explosion will be a celestial spectacle unseen in human history. It will not be a faint point of light. For a period of several months, the supernova could shine with the brilliance of a full moon, a second, intensely bright celestial object punctuating the night. It would be starkly visible during the day, a persistent and undeniable beacon in our sky. This would be more than just an astronomical event, it would be a global experience, a once-in-a-millennium phenomenon that would fundamentally alter our relationship with the cosmos, reminding everyone who looks up that the stars are not permanent, but are living, dying, and sometimes ending their lives in the most spectacular fashion imaginable. Even the most massive stars we see today are dwarfed by the primordial giants of the early cosmos. The first generation of stars, known as population 3 stars, were true leviathans, behemoths that could have contained several hundred times the mass of our Sun. Their deaths were not like the supernova or hypernova of the modern universe. They were something far more absolute, a theoretical cataclysm known as a pair instability supernova. Within the core of one of these monsters, the furnace burned at a ferocious, almost nonsensical temperature. The energy of the gamma rays produced by fusion became so unimaginably high that they spontaneously began to transform. Inside the core, a photon of light would spontaneously create a pair of particles, an electron and its antimatter counterpart, a positron. This act of creation is also an act of theft. Light itself, which provides the outward radiation pressure holding the star up, is literally being converted into matter, draining the energy that supports the star's immense structure. The core suddenly loses its internal support. With the pressure gone, gravity wins an instantaneous and total victory. The entire star does not just collapse, it undergoes a runaway thermonuclear implosion. The heat from the collapse triggers the fusion of heavier elements all at once. In a single, unstoppable chain reaction, the release of energy is so complete, so utterly violent, that the entire star is obliterated. There is no remnant, no neutron star or black hole left behind to mark its grave. The star is completely and utterly disassembled, its entire being blasted outward in an expanding cloud of newly forged elements. These explosions were so powerful, they likely seeded the early universe with the first heavy elements, the raw ingredients for everything that would follow, from rocky planets to living organisms. A pair instability supernova is the universe's ultimate self-destruct button, a blast of such pure fury that it leaves no corpse, only the scattered atoms of its own existence. That initial blinding flash of a gamma ray burst is merely the opening salvo. The true scientific treasure arrives in its fading echo. For days, and sometimes even weeks after the primary explosion vanishes from gamma ray detectors, a lingering afterglow continues to shine across the electromagnetic spectrum. This is the cosmic equivalent of a fireworks smoke trail, a brilliant and evolving remnant that tells the deeper story. This afterglow is born from violence. The ultra-relativistic jet, still screaming outward at near light speed, violently plows into the thin gas of the interstellar medium. It is a cosmic traffic jam of unimaginable proportions. The jet slams into this material, and in doing so, it creates a powerful shockwave that heats the gas to incredible temperatures and accelerates particles within it. This frenetic interaction causes the surrounding material to glow, first in X-rays, then in visible light, and finally in radio waves, each wavelength revealing a different piece of the puzzle. Without this multi-wavelength fingerprint, a gamma ray burst would be little more than a fleeting, unlocatable mystery. The brief gamma ray flash alone is not precise enough to pinpoint its origin. It is the long-lasting afterglow, shining like a cosmic flare in the darkness, that allows telescopes to swivel to the exact spot and capture its light. By analyzing this fading light, astronomers can perform a form of cosmic spectroscopy, splitting the light into its constituent colors to find the telltale signatures of distant elements. This data reveals the burst's redshift, a measure of how much the universe has stretched since the light began its journey, which tells us its mind-bending distance. It also allows them to identify the host galaxy, showing whether these monstrous explosions prefer certain types of galaxies, like those actively forming new stars. The afterglow transforms a mysterious blip of energy into a detailed cosmic biography, written in the fading light of a dying star's final, focused scream. Those ghostly neutrinos may hold the key to unlocking the universe's deepest secrets. When the next galactic supernova arrives, the pulse of these particles will be a flood, not a trickle. Modern detectors like Supernovae, and in Japan, and the upcoming Deep Underground Neutrino experiment in the United States are poised to capture not 24, but tens of thousands of these elusive messengers. Why does this matter so profoundly? Because the journey of these neutrinos from the collapsing stellar core to our detectors is a race against time and a dance of identity. Neutrinos are shapeshifters. They exist in 3 different types or flavors, and as they travel, they oscillate, seamlessly transforming from one flavor to another. The precise timing of their arrival, spread across a few tens of seconds, and the specific mix of flavors we detect creates a detailed fingerprint of their journey. This fingerprint is exquisitely sensitive to the properties of the neutrinos themselves, particularly their tiny but non-zero masses. Measuring this signal could finally pin down the exact mass hierarchy of these particles, a fundamental question the standard model of physics cannot answer. But the potential revelations go even further. The extreme conditions inside a supernova core are a natural laboratory for physics we cannot create on Earth. If exotic, undiscovered particles, like sterile neutrinos that do not interact through any known force except gravity, are produced in the blast, their subtle signature might be etched into the neutrino data. We are essentially waiting for a cosmic experiment of unparalleled scale to go off in our backyard. A galactic supernova would be a tragic death for a star, but for science, it would be a once-in-a-lifetime data windfall, a direct message from the heart of a collapsing core that could rewrite our most fundamental understanding of reality. The fate of a star is written in a single, elegant number, 1.4. This is the Chandrasekhar limit, the ultimate weight limit for a certain kind of stellar corpse. It was a young physicist, Subramanian Chandrasekhar, who first realized this profound truth during a sea voyage from India to England in the 1930s. While others believed that all white dwarfs, the burnt-out cores of sun-like stars, could remain stable forever, his calculations revealed a more dramatic destiny. He discovered that a white dwarf is a cosmic balancing act. It is supported not by the fires of nuclear fusion, but by a quantum mechanical effect, the sheer pressure of electrons being squeezed together. This pressure can only resist gravity up to a point. That critical point is a mass of 1.4 times that of our Sun. Any white dwarf pushed beyond this limit, whether by merging with another or by slowly siphoning material from a companion star, can no longer hold itself up. The consequences are instant and total. The increased pressure and temperature ignite carbon fusion simultaneously throughout the entire star. This is not a gentle burn, but a runaway thermonuclear chain reaction. In less than a second, the white dwarf is completely consumed, torn apart in a blaze of atomic fire. This is the engine of a Type 1, a supernova. Because this critical mass is always the same, the explosion's brightness is incredibly consistent, a standard candle that allows us to measure the vast expanses of the cosmos. A simple number, scribbled on a page nearly a century ago, governs one of the most powerful and useful explosions in the universe. Peering into the edge of the observable universe is like reading a cosmic history book written in fire. Our most powerful observatories, from the Hubble Space Telescope to the new James Webb, act as time machines, capturing the light of supernova and gamma-ray bursts that have been traveling for over 13 billion years. Witnessing such an event is not merely observing a distant explosion, it is looking back to a time when the universe was a mere infant, only a few 100 million years old. The light from these ancient cataclysms carries within it the chemical fingerprints of the earliest stars. When astronomers split this ancient light into a spectrum, they can read the specific signatures of elements present in the blast. Finding heavy elements like oxygen or carbon in a 13-billion-year-old supernova tells a profound story. It means that the very first generation of stars, the population 3 behemoths, had already lived, died, and seeded the pristine cosmos with the raw materials for rocky worlds in an astonishingly short period after the Big Bang. Each distant flash is a data point in the universe's childhood photo album, revealing how quickly it grew up and began the work of building complexity. Observing a gamma ray burst from such an unimaginable distance is an even greater technical marvel. These events are so phenomenally luminous that they act as brilliant beacons, illuminating the dark, gaseous highways of the early cosmos. As the burst's light passes through ancient clouds of hydrogen and helium, specific wavelengths are absorbed, creating a unique barcode in the afterglow. This barcode allows scientists to map the structure and composition of the intergalactic medium at a time when galaxies were first beginning to coalesce. It is a direct probe of the universe's toddler years. The very fact that we can see these explosions from so far away forces a humbling realization: the universe was already manufacturing titanic forces and forging the elements of life almost from the very beginning. The seeds for everything we know, including the atoms that make us, were being sown in those first, violent generations of stellar death. On Christmas Day 2010, astronomers received a cosmic present that defied all wrapping. A gamma-ray burst designated JARB 101225A, soon nicknamed the Christmas burst, flared in the distant cosmos. It was an event that seemed to break the established rules, a puzzle wrapped in an enigma. Its initial emission lasted for nearly half an hour, an eternity for a typical gamma-ray burst, and its afterglow was unusually red and faint. The data presented a mystery that sent theorists scrambling. One compelling, almost poetic idea suggested we were witnessing a deeply personal catastrophe. What if a wandering asteroid, or even a small planet, had been torn apart by the immense gravity of a neutron star? The scenario was one of ultimate destruction, with the rocky body being shredded into a glowing, hot disk of debris before finally spiraling into the stellar corpse, releasing a prolonged tantrum of energy. Yet another hypothesis pointed to something even more exotic: a rare kilonova, the merger of two ultra-dense objects. The long, smooth decay of the light curve seemed to fit, suggesting the radioactive glow of heavy elements forged in a stellar collision. For years, the true nature of the Christmas burst remained a subject of lively debate, a celestial whodunit. The eventual consensus leaned toward the kilonova model, possibly one involving a neutron star and a helium-rich companion. This single, strange event perfectly illustrates the complex detective work that defines modern astronomy. It is not enough to simply see a flash in the sky. Scientists must become cosmic forensic experts, piecing together the story from the fading clues of light, duration, and color, proving that even the most energetic explosions in the universe can arrive wearing a clever disguise. A supernova's fury echoes far beyond its own stellar neighborhood, shaping the destiny of its entire galaxy. These explosions are not merely endpoints, they are master regulators in a grand cosmic ecosystem. This process, known as supernova feedback, acts as a fundamental check on a galaxy's growth. Within a bustling stellar nursery, new stars are born, but the most massive among them live fast and die young, exploding as supernova within just a few million years. When they do, their collective shockwaves and intense radiation heat the surrounding clouds of cold, dense gas. This is the raw material for future star formation, and by heating it, the supernova essentially scatter the stellar nursery's building blocks, preventing that gas from easily collapsing to form new stars. It is a self-regulating cycle where one generation of stars actively limits the birth of the next. Without this feedback mechanism, galaxies would gorge themselves on their own gas, forming stars at a frantic, unsustainable rate. They would become impossibly large, bright, and dense, filled with countless stars, but we do not see many galaxies like that. The observed size and structure of galaxies, including our own Milky Way, are a direct result of this balancing act between gravity's pull and the explosive push of supernova feedback. The influence goes even further. In smaller galaxies with weaker gravity, the cumulative energy from multiple supernovae can be so immense that it does more than just heat the gas, it can blast it completely out of the galaxy. Powerful galactic winds, fueled by these repeated explosions, can sweep entire reservoirs of star-forming material into the vast emptiness of intergalactic space. This effectively halts the galaxy's growth, leaving it a quiet, aging system. The expelled gas, now rich with the heavy elements forged in those stellar explosions, travels for eons, eventually mixing with the pristine hydrogen and helium of the intergalactic medium. This is how the space between galaxies, once a void of only the lightest elements, becomes seeded with the oxygen, carbon, and iron necessary for rocky planets and life. Every supernova is a local catastrophe with a galactic scale impact, a single voice in a chorus that dictates the structure, size, and chemical richness of the entire visible universe. The ocean floor holds a secret archive of cosmic violence. Miles beneath the waves, in the layered sediments of the deep sea, scientists are hunting for the fingerprints of long-dead stars. They are not looking for light, but for atoms, specifically a rare radioactive isotope called iron-60. This particular form of iron is a cosmic calling card, forged almost exclusively in the heart of a supernova and blasted into space by the explosion. When this stellar debris drifts through our solar system and rains down on Earth, a tiny fraction settles onto the seafloor, buried over millennia. By extracting deep-sea cores and analyzing these ancient layers with incredible precision, researchers can pinpoint moments in Earth's distant past when our planet was dusted with the radioactive ash of a nearby stellar death. The data paints a startling picture. There is a clear spike in iron-60 concentration in sediments dating from around 2.5 million years ago. This is not a single event, but evidence of a sustained shower, suggesting our solar system was drifting through the expanding debris field of not one, but an entire cluster of supernovae. This celestial fallout did not just land in our oceans. The same iron-60 signature has been found in samples of lunar regolith brought back by the Apollo missions, confirming that the entire inner solar system was bathed in this radioactive rain. These deep sea crusts and moon rocks are more than just geological samples. They are a fossil record of our local cosmic environment, proving that we have sailed through the turbulent aftermath of stellar cataclysms. The universe outdid itself in October of 2022. A wave of pure energy, now known as JRB 221009A, swept through our solar system. It was so blindingly powerful that it earned the undisputed title of the BOAT, the brightest of all time. Even originating from a galaxy nearly 2 billion light-years away, its ferocious intensity was enough to overwhelm and saturate gamma-ray detectors on multiple spacecraft. For a few fleeting minutes, this single event carried more energy than our Sun will emit across its entire 10 billion-year lifespan, but the spectacle was far from over. As the initial blast faded, its light began a second, slower performance. The powerful X-rays from the burst traveled across the void and began illuminating vast, dark clouds of interstellar dust within our own Milky Way. Each dust cloud acted like a cosmic mirror, reflecting the X-ray light back toward us with a slight time delay. Over the following weeks, space-based observatories watched as a series of concentric rings of X-ray light, like ripples from a stone dropped in a galactic pond, expanded outward from the burst's location. This rare light echo provided a unique three-dimensional map of the dusty structures hidden within our own galactic neighborhood. For scientists, the BOIT was a data bonanza of unprecedented scale, a once-in-10,000-year event that delivered a masterclass in high-energy astrophysics. Every facet of its emission, from the initial pulse to the fading afterglow, is being meticulously studied, forcing us to refine our models of how these cosmic engines truly work. This single burst reminds us that even our most extreme theories can be humbled by the raw, untamed power of the cosmos. Our understanding of cosmic violence is no longer limited to what we can see. We have entered a new era of perception where we can now hear and feel the universe's most powerful explosions. This is the age of multi-messenger astronomy. Before, our knowledge came almost entirely from light, from the photons that traveled across the cosmos to our telescopes, but light is only one messenger. Now we can detect the ripples in space-time itself, the gravitational waves generated by the collision of neutron stars. We felt that for the first time in 2017, a literal shudder in the fabric of reality that announced a kilonova. At the same time, we are building observatories to catch the ghostly neutrino pulse from a supernova's core, a direct feel of the engine at the heart of the blast. Each messenger brings a unique piece of the story. Light shows us the heat and the chemistry. Gravitational waves reveal the dynamics of massive objects moving at incredible speeds. Neutrinos provide a direct, unfiltered telegram from the deepest, most hidden regions of the explosion. By combining these signals, we are no longer just watching a fireworks display from a distance. We are standing in the room, feeling the concussive blast and hearing the roar, while also seeing the brilliant colors. This multi-pronged approach is transforming a two-dimensional picture into a full, immersive experience. It allows us to test our most fundamental theories of physics under conditions we could never hope to recreate. What other secrets will these combined messengers unlock as we learn to listen to the full symphony of the cosmos? From the forges of supernova to the focused scream of gamma-ray bursts, this journey has revealed a cosmos defined by its violence. These are not random acts of destruction, but the fundamental engines of change. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all forged in these stellar furnaces and scattered across the galaxy by their explosive deaths. The gold in a ring, the silicon in a computer chip, every heavy element that makes our world possible is a direct result of a star that died long ago. We are quite literally the children of these cosmic cataclysms. The universe's greatest acts of creation are born from its most energetic explosions. So the next time you gaze up at the seemingly tranquil night sky, remember the truth. You are looking at a dynamic and often violent arena, a continuous cycle of death and rebirth happening on an unimaginable scale. That quiet speck of light might be a star on the verge of its own spectacular end, destined to someday enrich the cosmos with the seeds of new worlds and, perhaps, new life. We want to hear what amazed you most on this journey. What fact about these cosmic explosions reshaped your view of the universe? Share your favorite discovery in the comments below. This grand cosmic drama is not just for professional astronomers to witness. You can become a cosmic explorer yourself, joining the global hunt for these fleeting, violent events from the comfort of your own home. Online platforms like Zooniverse connect the curiosity of the public with the vast, overwhelming streams of data from the world's most powerful telescopes. These projects are not mere games. You are presented with real images of distant galaxies, and your human brain, with its incredible pattern recognition skills, can spot the subtle, new point of light that signals a supernova's arrival. Every click is a genuine contribution, helping scientists sift through the noise to find the celestial needles in the cosmic haystack. you could be the first person to ever lay eyes on a star's final, brilliant death cry in a distant galaxy. The link to get started is waiting for you in the video description below. This is your invitation to move from being a spectator to an active participant in the greatest story ever told. Your observations help build the timeline of cosmic violence, mapping where and when stars die, which in turn helps us understand the life cycle of galaxies. You are not just learning about these explosions, you are helping to discover them, adding your own piece to the grand, unfolding puzzle of our universe.